This next section, continuing after the Rutherford model, replaced the Thomson model of the atom. We want to discuss section 40.2, the Bohr model of the atom. Now, in 1913, this is 2 years after Rutherford made his discoveries, Bohr proposed a model of the atom with quantized orbits and discrete transitions. Well, this is what we had observed. We had already seen that if we had an atom consisting of all these protons and positive charge that was concentrated, and the electrons moved around, for a given atom, these electrons could only move in certain orbits, and not a continuous spiral in as what we would think classically that would happen, and which was not observed at all. So if an electron were in this orbit, excited here, it could drop down to a lower energy, down to here, and begin to rotate, and at the same time that energy would go off as a discrete frequency, and this frequency would be the difference of the two, determined by the difference of the two energies here. How did he determine what these quantized orbits were? Well, he did something very interesting. In studying the energies that were available, he concluded that if the angular momentum is quantized, the angular momentum, you recall, is r cross p from last semester, which is the radius out. If I have something moving around in a circle, it's the radius out times the momentum that's in the perpendicular direction. So that's the radius times p, the magnitude of r times the magnitude of p times the sine of the angle theta, which is this angle here between the two, and that gives the projection of p in the perpendicular direction, not the parallel direction. So it's p perpendicular, that's p perpendicular, times the distance out. This gives us our angular momentum. And of course, in classical mechanics, angular momentum is continuous. So what he is proposing is that the angular momentum was an integer multiple of Planck's constant divided by 2 pi. This expression occurs so much, we now give a symbol to this, and we call this h over 2 pi, we call it h bar. So L is nh bar, and h bar is Planck's constant divided by 2 pi. And you should remember that because it's what is used almost exclusively in quantum theory. By Bohr's proposal here, he was able to show that this would in fact lead to the energies that we would get, but he had no idea why this was true. Now, how would this lead to certain energies? Well, you could take the angular momentum and force what was previously any radius could have the electron rotating, but now only certain radii could occur since we get the equation from here that r times p perpendicular must equal to an integer times Planck's constant. Given a given radius, we now know exactly what the momentum has to be, but the momentum has to balance the centripetal force. So in fact, you have two equations. You have this one, this equation, this is the equation that results from Bohr. And you have another equation that balances the centripetal force that we'll talk about in just a moment. So this gives us our fixed orbits, and Bohr showed that this actually worked. But he had no idea why it worked. Why would the angular momentum only occur in these quantum amounts?